Okay, so hey everybody. So I'm just delighted to be able to tell you about this stuff today, and really thanks for coming. So before I start, I'm going to pass out a couple demos, and so everybody's going to get a sheet of Mylar. This is the stuff that potato chip bags are made out of, at least the cheap kind. And so everybody's going to get a sheet of Mylar. So please start sending those around. And thanks, Rana. And also, everybody gets a paper clip. So we only have one box of paper clips, so we'll just have to get that around the whole room. And I don't want you to do anything with them yet. Just hold on to them. Could clip the paper clip to paper so it doesn't go anywhere. Okay. So I am a soft matter experimentalist. That's the label that also applies to Irmgard, and you saw the wonderful things that soft matter experiments can do. And I'm going to tell you about two more today. This is an air bubble underwater, and this is a suspension of particles in a very viscous liquid. And they both have weird and wonderful memory properties in addition to other cool behaviors. And I guess before I start, I want to put in a plug. So I'm from Cal Poly, which is just 90 minutes north of here on the 101. And Cal Poly is the proud home of the STAR program. And this is a program that gives pre-service teachers, so people doing their bachelor's degrees who want to go into teaching, or people in certificate programs, it gives them authentic research experiences at a whole bunch of really amazing lab sites throughout the country. And this is something, so if you know a pre-service teacher, you really should make sure they know about this, right? So this is a full-time, paid, 9-week summer research opportunity, and they structure it so that teachers really get the tools they need to then translate this back into the classroom. So it's an awesome program, and I just want to put in a plug for it. Okay, it's not just for Californians. Okay, so I'm really interested in memory, which is great because that's what this program's about. And how I define memory is that you put information into a system, and then at a later time you can recover it. And it's a really great, as Sue was kind of getting at this morning, it's a really great language for talking about how systems depend on their initial conditions and their history, or aspects of that dependence. And it's also a really great way to explore just the nature, sort of the basic physics of a system or material and its dynamics. It tells you something about that material itself. Okay, so I can think of a few requirements. We're going to talk about memory and materials, I can think of a few requirements. And Sue kind of went over these too. The first one is you have to have many degrees of freedom. And that's just a fancy term for you have to have a system or material that's described by a lot of different variables. And usually, if you have a material, that's not a problem because it has lots of atoms in it, right? And each of those atoms has an XYZ position and velocity. So by definition, most materials have lots of degrees of freedom. And it also has to be changed by external driving, right? Otherwise, how would you put the information in? You have to have some way of driving the system. And so soft matter, this is a study of deformable things, is a great place to find memory because by definition everything is soft. It can be deformed. It responds to driving. Okay? And the third test that's really important is that your material can't relax to equilibrium. Right? And so if I have, so I've got a little dish of water here on my overhead projector, and yes, it has lots of degrees of freedom. There are zillions of molecules in there, or at least a lot. And it responds to driving, right? I can poke it, and I make little waves. But if I just wait a few seconds, it's flat again, right? It relaxed back to equilibrium. And no one would be able to tell that I was just making waves on this water, right? And so it's that third test, or really all three, that are really important for talking about memory behavior. Okay, so what I'm going to do, I'm going to tell you about slow memory first. And to do that, I'm going to introduce this topic of cyclic driving and systems that respond to it. I'm going to then tell you about a particular interesting material that responds to cyclic driving, which is suspension of particles in liquid. And then I'm going to switch gears and talk about fast memory and try to challenge everything that we've learned. Okay, so what do I mean by slow? Well, cyclic driving is everywhere in our world. So we have seasons, we have day-night cycles. Lots of things are driven cyclically. Here are traffic driving over a bridge, right? And just thousands of cars every day over and over and over again, right? And we also have cyclic driving for our minds, right? If we're learning a new skill, we have to practice it many times before we get the hang of it. And systems can be gradually changed by cyclic driving, right? This bridge, over the years, over millions of cars driving across it, is gradually changed by that. And similarly, you would hope that your brain is gradually changed by doing something many times. Okay, so we also have the possibility that if you have to do something for many cycles in order to imprint it on the material or a system, that also gives you the opportunity to do something a little more complex, because if you have many cycles to do this, you could maybe change the input and do different inputs on different cycles, and maybe your system could learn more than one thing. So that's a possibility that's going to be really important later on in this talk. Okay, but first I want to think about specifically how does cyclic driving change a system gradually. Okay, so we're going to start with one demo. Unfortunately, it's one that you're not holding in your hands. Okay, so well, that was a bad idea. Okay. Okay, great. So what you see hanging from these this hemostat here. All right, so first of all, I've got a good old force gauge here, and I've got this hemostat, and hanging from it is a strip of ordinary rubber that I bought from McMaster Carr. That's really where all good science experiments come from. Irmgard alluded to that. And so this piece of rubber is about 7 inches long, and I'm going to stretch it by an additional 9 inches. So I've got a mark here on my meter stick, 33 inches. I'm going to pull it down to that and let go. Okay. So before we think about what's going to happen, let's talk a little bit about this rubber itself. Okay, so rubber, as you know, is made up of lots of polymer molecules, right? Flexible polymer molecules, carbon and hydrogen and so forth. But that's not what makes rubber rubbery. What makes rubber rubbery is that these long polymer molecules also have very short little cross-links that link one molecule to another. Okay, and this cross-linking is done after the fact, right? And as a final step in manufacturing, it makes it rubber. And these cross-links make this very resilient network, but the cross-link bonds are typically disulfide bonds, and they tend to be weaker than the original molecules, right? So it's kind of the weakest link in this material. And so when you stretch a piece of rubber, like I'm going to do, you're tugging on all of these polymer molecules, but you're also tugging on the cross-links. Okay, so I want you to keep that in mind, and now I'm going to ask you, again, before I do this, I'm going to do something that I like to do with my students, and you may do with yours. So I'm going to ask you what should happen after repeated stretching. Not the first time, but the second, third, fourth times. And how we're going to do this is I'm going to show you 4 possible answers to this, and we're going to have you vote. So you're going to look at those 4 answers. You're going to think about it silently, just by yourself. And then you're going to vote, and the voting is going to be simultaneous and anonymous. So I'll tell you how to do that in just a minute. And so first let me show you the possibilities. I think you can read that last one there. So I'd like you to read these and come up with your best guess.
You're going to double the length of the rubber.
I'm going to effectively double the length, more than double the length. Yes. Okay, so we're going to vote right now. And how this is going to work, you see 4 choices up here. Everybody in this room, I think, has at least 4 fingers. And so what you're going to do is hold up the number of fingers that, when I say so, not yet, you're going to hold up the number of fingers corresponding to the answer. And that's going to be simultaneous. It's on my signal. And it's also going to be anonymous. You're going to hold your fingers down here because I want to see them, but we're not really going to advertise what your vote is. Okay, so everybody knows how many fingers they're going to hold up? On 3, 1, 2, 3. Interesting. Okay. We are all over the map. This is great. Okay, so what I would like you to do, but not, okay, it's not like wild. What I would like you to do is turn to someone sitting next to you, say hi. They're probably wearing their name, which is great. And I want you to convince them that you're right. Find out what they think and then convince them that you're right. Got about a minute. Okay. Okay, so we're going to vote a second time now that you've had a chance to think about it a little more and talk it over. And again, this is going to be simultaneous anonymous. So on 3, so decide how many fingers you want to hold up, and on 3 we're going to do that. 1, 2, 3. Whoa. Okay. So it looks like the most popular answer is 2. But that's not unanimous. Okay, so we're going to see. Did
it change?
We haven't done anything yet. Oh, did the most popular answer change? Yes, more people chose 2. Okay. That doesn't mean more people are right. We're gonna see. Okay. Sorry? 2 and 4 could be, yes, 2 and 4 could be simultaneously true. So some people did choose 4 as well. Okay. Of course, it could break on the first try, but I probably thought of that. Okay, so, all right, so I've got good old Logger Pro up here, and we're going to try this now. So we're just collecting force versus time. And remember what I'm going to do? I'm going to stretch this down to the 33 mark on my ruler, and we'll do that 3 times. Okay, so we're collecting data, yes? All right, here we go. And back up. And then we'll do this again. And now the 3rd time is really important. All right, and now I'll let go. Okay. So let's try it a couple more times. All right, so that's the first time. Oh, I can turn on the auto scale here. Might as well do it just a few more times for good measure. So pull it down to 33. Let go. 33. Let go. 33. Let go. Okay. So, what do you think?
Now I'm confused.
Now you're confused. Why are you confused?
I thought that
Yeah. Okay. So most of the crosslinks decayed on the first time.
Had it been stretched before?
It had not been stretched before, at least not by me. Who knows what's going on at the warehouse? Yeah, so most of the crosslinks break the first time, but every time I do it again, I break just a few more. And you can see that. So I think the answer may depend on interpretation, but it's definitely continuing to change just a little bit.
What would happen
Okay.
if you stretch it 1,000,000 times?
1,000,000 times, then it had better start doing the same thing, or break. Yeah. Okay, so let's try a few more things here. Go back to the slideshow. I think I have to unplug this or it's going to destroy my battery. Oh no, that's not good. All right, great. Okay, by the way, if you want an example of doing something again and again that doesn't change a material, you can just hang a mass from a spring. This thing can go up and down for thousands and thousands of cycles, and you won't be able to tell that this spring has been used before. Right? So it's possible to make systems that respond to cyclic driving without changing at all. Okay, so let's bring this down. Okay, great. So, oh yeah, so you've all got paper clips by now, right? No? All right, we'll keep them going around. And maybe we'll do this. Maybe we'll do this near the end. All right, so let's try something else. Okay, so do you all have Mylar sheets? Yeah? Okay, great. I've got one here. All right, so I think after, so Arvind had this beautiful talk where he showed that if you precisely pattern the creases in a material, a sheet, and you control the angles very nicely, you can encode an incredible amount of information with specificity. But then you probably tried to do it yourself, and it's hard. Okay, it's really, really fiddly. All right, so I think we could all use a moment of catharsis if we just take our sheet and crumple it. Okay. Okay, so we're just going to do that once. And now the question is, okay, so you made some creases and some little dimples in this sheet. We call them D-cones. They're little defects. And this is my question for you. I want you to think about this, and then in a minute we'll vote. Don't do experiments. Oh my gosh. What is this? What kind of scientists are you? All right. All right, so decide which choice you want to do, 1, 2, or 3. And on 3, you're going to hold up that number of fingers. Okay, 1, 2, 3. Whoa, okay, a lot of diversity here. I was not expecting a lot of diversity. So let's turn to your neighbor, and you've got just a minute to convince them you're right.
If you can hang out on that side, that's good too.
Oh, sure. Whoops. Okay. I think we should vote one more time. So decide what you want to do, and on 3, 1, 2, 3. Okay, great. All right, so there are no more ones, which is good. People change their minds under new information. But there seems to be some disagreement about whether you will ever stop making new creases. And guess what? This is actually a subject of disagreement among people researching this. Okay? So some experiments say one thing, other experiments say other thing. We know that you'll make fewer and fewer new creases as you do it again. But the question is, will you ever have the right set of creases so that it always reuses existing ones? I don't know. Okay, so you can see that response to cyclic driving can be kind of a tricky thing, right? And I don't think we have time to do the paperclip experiment, but you can probably guess what happens to a paperclip if you bend it repeatedly. Things go a little differently for the paperclip. Okay, so it can be a very tricky thing, and the specific reasons that a material has some specific response can actually be pretty cryptic. Okay, so all right, so we get to what's called a steady state, but maybe only approximately with our creases. Okay, so the next thing I'm going to tell you about is something that is a little bit quieter than Mylar. It is particles in viscous liquid. Okay, so this is work with Sid, who's sitting back there, and also Joey Paulson, who's now at Syracuse University. So, first, before I tell you about this system, I have to teach you some definitions. Okay, so you can take any material and apply a shear stress to the top surface. Now, a shear stress is just like a pressure in that it has units of force per area, except that pressure is applied normal to a surface. Shear stress is applied tangentially. Okay, so we apply a shear stress, and now it deformed the material, right? And we're going to measure how much we deformed it. So to do that, we have a really clever way to do that. We measure how far the top of the material moved, and we divide by the thickness. And so then you get a dimensionless number that's independent of the size of your material, and this dimensionless number is called strain. It's just the tangent of this little angle here. Okay, so we use gamma for strain. And the last thing you need to know is often we test materials or otherwise probe them by doing what's called oscillatory or cyclic shear, where we shear a material back and forth repeatedly, and we do it with some amplitude, gamma naught. Okay, so all right, so now you know what those are. By the way, see Maggie on your way home today. She'll give you a State of California engineering license. Okay, so this is now the material that we're going to work with. This is some acrylic beads in a viscous liquid. It's very viscous. The main ingredient in this liquid is basically pure high-grade laundry detergent. This is really viscous stuff. And these bead diameters are a little less than a millimeter. And so, normally you think of particles in liquid, you think Brownian motion. That is not happening here. There's no diffusion. Okay, so.
Does gravity pull them down?
Yes, we carefully added zinc chloride to this liquid so that it is exactly the same density as the acrylic. So they should not be going up or down. Okay, so we're going to use an apparatus called a Couette cell to do something with this liquid. This is two concentric cylinders, and the gap in between these two cylinders is going to be filled with our particle goop. All right, now this is that same apparatus viewed from the top. And the trick here is that we have an inner cylinder that rotates, and it rotates back and forth, right? It oscillates cyclically. And we keep that outer cylinder fixed. And so if you think about that little diagram I had before, there's our little piece of this material, and it's getting sheared back and forth. Oh, I guess I should have flipped this around. The inside part is getting pushed back and forth as this inner cylinder rotates, right? And the outer part is fixed. Okay, so everybody kind of follow what I'm doing. Okay, you have to get this. Okay, great. Oh, and then we put our camera right here, and we look through the outer cylinder into the suspension. We see the particles. All right, so I'm going to play a movie for you. Before I play the movie, though, I got to tell you a little secret. So Irmgard showed you how transformative it can be to make some part of your experiment that was invisible visible. Okay, but we made this experiment better by making most of it invisible. So the particles that you see are only 0.5% of the actual number of particles in this picture. Okay, so it's actually 30% particles by volume. And the reason that we did this, that we can do this, is that not only did we match the density of the acrylic, but we also matched its index of refraction, right? And so these curved spheres of acrylic would normally refract light, and that's how we would see them. But they don't if the medium outside them is matched. Okay, but I took 0.5% of these particles, and I went to Walgreens and bought some RIT, and I dyed them black. Actually, I tried, and then I read the instructions, and then I dyed them. Okay, so this is what we see. Okay, so what's going on here? Well, some of the particles aren't moving, and that's because those are the particles that are really close to this outer cylinder right here. The outer cylinder isn't moving, so the particles that are close to it should not be moving. And then some of the particles are going back and forth with a large amplitude, and those are the ones that are close to this inner cylinder. Okay, so this whole suspension is getting sheared back and forth. We're just looking at it from a weird angle, right? So the particles in front are not moving, the particles behind them are moving. Okay, so this should probably remind you by now of that really cool demo that Sue did this morning, right? Where she had that cylinder, she rotated, and she brought it back, and that blob of dye came right back to where it was. And that should be about what you see here. These particles seem to be coming back to their starting positions. So what does that mean? That means that if we took a picture now, and another picture now, and another picture now, if these particles are coming back to the same place, we will be making the world's most boring movie. Okay, so let's play the world's most boring movie for you. This is now an image of these particles, and we're sampling stroboscopically once per cycle. And so these particles should not be moving. Okay. So, what is going on? All right, why are these somehow agitated? So you can kind of explain what's going on with a very simple model that works surprisingly well, and this was thought up by Laurent Coté and his collaborators. And the idea is that you put some particles in a box, you shear the box, just like we've been doing with this liquid, and you look for particles that touch each other, that overlap, that collide, while you're doing that shear. And if you catch them doing this, the computer gives each one a random displacement. We don't know what is going on. We just know they're somehow perturbed by this collision. And then you repeat. You try again. And so what you see in this movie is these particles, remember, we're shearing it in between pictures. These particles are bumping into each other, and they're somehow perturbing each other. And that's what you see moving around. Remember, 99.5% of the particles in this picture are invisible. So those are probably the ones they're running into. Okay, so this is what happens in the computer when we apply the same model I told you about. We start out with the particles in random positions. And this group that came up with the model, they found that fewer and fewer particles over time are active, right? They eventually figure out how to get out of each other's way. And so if we were to make a graph of how many particles are colliding like this as a function of how many cycles we apply, we start with a lot of particles colliding because they're in random positions, but then we're applying a shear amplitude or strain amplitude of 3 over and over and over again. And eventually, they all figure out how to stay out of each other's way, and that's the end. After that, everything comes back to where it was. Okay. Well, that's great, because it means that we have stored a memory in this material. And to see that, imagine that I do this, okay, and then I leave the lab, and you come into the lab, and you have to figure out what strain amplitude I was using, right? I'm sending you a message, 3. That's where we're going to meet for dinner. Okay, so system remembers the strain amplitude that was applied repeatedly. And in order to read it out, what you do is you shear the system to a strain of 1. And you're like, oh, okay, no particles collided. Everything comes back to where it was. Now you're going to shear it out to 2. Again, no collisions. 3, no collisions. That's what I've been training it with. But then you go to 3.1, and you see particles all of a sudden start to collide, and they're now moving around again. And so you can figure out what strain amplitude I've been using. It's a memory. Okay, it turns out you don't even need to wait for 60,000 cycles or whatever to get there. After just 100 cycles or less, you could make a graph like this, and you see this little kink here that tells you where the memory is. Okay. So, fortunately, I got to skip this. You can actually read this out. You can feel when these particles start to collide. So we're looking at stress here. And you can actually feel, or the machine that's doing this can feel when they start to collide. You can read out this memory mechanically. All right. And there's our signal. All right. So that's not what I really want to talk about. I want to talk about this opportunity to put multiple memories in the system. So what if we, instead of doing just 3 again and again and again, we do a pattern with 3 and then 2, 2, 2, 2, 2, and then 3 and then 2, 2, 2, 2, 2, over and over. And what you see instead is that after just 100 cycles, now there are 2 kinks in here. Right? So the particles are trying to get out of each other's way for a strain of 3, but at the same time, they're also working on 2. And they've made progress on both, and you can see both there. Okay, but there's a catch, because as you keep going, the final state is the same. These particles don't want to run into each other at all. And the only way they can do that is to get out of each other's way for all strains that we're going to be applying. And that means this curve is going to be 0 until we get to 3, and then they'll start moving. Okay. So the final state is the same as if we were doing just one memory. This second memory is forgotten. All right, so that is weird. And let's actually see if this works as an experiment now. So I started these experiments, but Joey Paulson's the one who actually got them to work. So we're doing these 2 strain amplitudes, 1.6 and 0.8. We have a more sophisticated way of getting out this memory signal by looking at how these particles move. We repeat the pattern twice, and lo and behold, there are 2 memories. We repeat it 3 times and 12 times, and it's like that smaller amplitude never happened, even though we told it the smaller amplitude more times. Right? Giving it the same input more times does not mean more learning. Right? It actually forgets the smaller one. Okay, so there's a clever way to get past this limitation. What if you can keep the system from getting to this final state? All right, how are we going to do that? Well, we just have to perturb these particles a little bit. They're trying to reach positions where they don't collide, but if we just figure out how to push them away from those positions just a little bit, then we won't reach this forgetting state at the end. And so what we do is we're going to pause 8 minutes between cycles of this experiment. And someone asked earlier about density matching, and I said they were density matched. Well, they're not perfectly density matched. Some of the particles are buoyant. They're going to go up in those 8 minutes. And other particles are going to go down just a little bit in those 8 minutes. And that's enough to keep us away from this steady state of death. And look at that. We applied the training 12 times, and both memories are in there. And it's because we added noise. Okay, so this is a weird system. We can learn multiple values of strain. After many cycles, it's going to forget everything but the largest. But you can fix that by making it noisier. Okay, here's the weird part. These same rules apply for memory of electrical pulses in charge density wave conductors. That's something I'm not going to tell you about today, but it's the same rules in a totally different system that's not wet at all. Right? It's electrical. And by the way, this is one of the reasons that Sue's a really big deal. She figured that out. Okay. So, are there other materials that this could apply to? And or how are they different, right? Part of that is what I'm doing in my lab at Cal Poly. So I'm working on disordered materials like mayonnaise and trying to think about what kind of rules apply there and why. And that was actually a hot topic at the conference this past week. Okay, not mayonnaise. We're not really doing experiments on mayonnaise, but materials like it. All right, so last thing I'm going to tell you about. You'd think that you need these complex non-equilibrium materials to get memory, but I'm going to tell you you actually need just air and water. Okay, air and water could not be more boring, right? Well, actually, you saw Irmgard's talk. Now you know they have some tricks up their sleeve. So what I'm going to tell you now, this is work with Sid, and then we worked with 3 wonderful theorists, all at Chicago at the time. So this is taken in my bathroom using the high-speed camera in my smartphone. Films at 240 frames per second. This is a dripping faucet. I was pretty pleased with how this turned out. You can see there's clearly something pretty intricate going on, and it's really fast. It's too fast for this, actually. But pretty nice picture. Okay. But instead of 240 frames per second, we can go at 22,000 frames per second. And now we're going to see this. Oh, and by the way, you saw Irmgard's talk, right? These bright spots are just because there's a light directly behind the drop, so it's acting like a lens. All right, so we'll keep playing.
Nathan, how do you do 22,000 frames a second?
You convince someone to give you a lot of money to buy a camera that does that. So ask Sid how to do that.
A film camera?
It's all digital. Yeah, this used to be done with film cameras, and yeah, we don't want to go back to that time. Okay, so this beautiful pinch-off, and it actually happens twice, right? It happened below and then above. Okay, now you don't actually need a camera that costs $100,000. You can do it with just a simple camera that takes only one picture. You just have to take that one picture at exactly the right time. Okay, so this is a picture I made in my lab at Cal Poly, actually, and the falling drop interrupted a laser beam, and that is what triggered the camera, and you actually see a trace of that laser light right here. Okay, so we have these 2 pinch-offs, and there's something really remarkable happening. The size of this little neck of water is shrinking down to 0, right? That's the only way we're going to break this, is we have to have this part that goes to 0 size. All right, and you look at the equations of hydrodynamics, and they tell you that some crazy bad things are going to happen. So as this radius goes to 0, you have quantities like the curvature, right, that we describe how tightly curved this is. Well, obviously, if it's 0 size, it's infinitely curved. It's 1 over r. Okay, but we also have a surface tension between air and water, And we know that surface tension really doesn't like tightly curved objects, and it exerts a pressure that is also diverging, right? This is surface tension over radius. And we have a diverging and infinite pressure acting on a smaller and smaller volume of fluid, and so you would expect the velocity is just going to go through the roof. That's why this is so fast. So that's also going to infinity. All right, and so the name we give to the moment when all these things appear to go to infinity is a singularity. Okay, so let's look again at these two singularities that we have in this movie. One is upside down, right? Gravity's pointing in the other direction. But it looks really similar. And actually, if we could just turn one of these over, you can see it really looks really similar. And now we're going to just put them on top of each other. And holy cow, they look almost identical. And the crazy thing is that the parts around them are not, right? But as you get close to where the singularity is happening, you can't tell any difference, even though gravity is the other way around. Okay, so the reason these are the same is something called universality. The idea is that your initial conditions and your boundary conditions, which is to say the stuff on the outside, like the faucet that this is dripping from, those are on large scales, right? Several millimeters or more. Your singularity is on the smallest scales. And so you can kind of intuitively get that the things on this big scale and low velocities, low pressures, are not going to have much impact on this tiny, tiny thing that's going at very fast velocities and very high pressures. And so the singularity forgets. It forgets the information that we put into this. And so this holds generally for a lot of pinch-offs. For a given inner and outer fluid, and we've got some wild ones here, all singularities everywhere ever are going to be the same, whether it's on Earth or upside down or from a weird-shaped nozzle or in orbit, anything. They're always going to be the same. Singularities work like that. Okay. So now I'm going to show you this dripping faucet, but we're going to turn it inside out. We're going to put the air on the inside and the water on the outside. All right? And so this is coming out of a nozzle that I drilled in a plate. This is all underwater. And I'm adding air to this bubble. You're going to see it get just a little too big. And it becomes unstable. Okay, so you can look at these capillary waves all day, but I want to focus on that moment where the singularity. That was really fast, by the way. That whole process took only 50 milliseconds. Okay, so this is that final moment. Looks nice and symmetric. And I'm going to try something. I'm going to tilt this nozzle that the air is coming out of. I'm going to tilt it by just 2 degrees. And since this is a singularity, it's universal. And that means that the effect should be absolutely nothing, right? Because that nozzle is on a large scale. It's very far removed from the singularity. By the time the dynamics reach that singularity, there should be no influence from whatever angle I was holding this nozzle at, or what direction gravity is. This is what we see. Okay, so it remembered. And we can see this effect for tilts as small as 0.5 degree. No, sorry, 0.05 of a degree. Okay. So here's the reason. I feel like I should explain this a little bit. So for this water drop, which was universal, the way that it does that, the singularity has to control what's going on above and below it. Okay? And the way it does that is that as this neck is pinching down, getting smaller and smaller, it's squeezing the water out of it. And the only place that water can go is up and down. And so that water squirting out from the singularity is how it basically controls and influences the region around the singularity. And that's how it gets the region around the singularity to do what it wants and not what the boundary conditions and initial conditions said. That's how it communicates and makes this universal. Okay, what if the inner fluid, which is air here, is basically insignificant, right? Air is insignificant, except if you're in Irmgard's talk. Okay, so this breaks universality, and that's how we get this. Okay, so I have just a few minutes left, but you kind of get the idea that I can do wild things with this singularity just by messing with the initial conditions. And I still get this divergence in velocities and pressures, so you know it's going to be awesome. Okay, so let's find something here to show you. All right, this is viewed from above. Oh, actually, I'll show you this first. Okay, so Laura Schmidt did the theory on this, and after she got her PhD, she moved to the Netherlands, University of Twente, and joined a group that did another amazing experiment related to this. So instead of blowing a bubble, they took a disk 2 centimeters in diameter, and this is our metal rod sticking down below the surface of the water. And there's going to be a motor that pulls this thing down into the water. And what's going on? Oh, here we go. Okay, so you get this nice splash. But below the surface of the water, we've created a cavity that's then going to collapse on itself and release this jet. Okay, so here's what it looks like below the surface. So we're basically creating an upside-down bubble, and it has to pinch off. There we go. Okay, so now let's put our camera above the surface of the water, looking down on this cavity as it's collapsing, and let's mess with the initial conditions, right? Instead of using a circular disk, let's use something with this threefold symmetry. All right, so what is this going to do? So we get this beautiful oscillation, right? It started out one way, and then by the end, where it's sticking out here, it's going to be sticking in at the end. Okay, and that's because Wendy and Laura figured out that the part that's sticking out more, this sort of curved part, the water has more opportunities to rush in to fill this cavity in this curved part that's sticking out. There's more directions that it can come from. And water is just inertial, right? It's going to overshoot. Of course it's going to overshoot. And so it's rushing in faster here. It's rushing in faster here. There we go. And so this part is now going to be the farthest in later on in the movie. All right, so let's try it with a 6-fold disk. And now you can see it's going to switch orientation once. And then right before the end, it does it again. Okay. So, I don't have time to go into this, but you could ask the question, could you take a snapshot right before it pinches off and somehow rewind the dynamics to find out what shape and size disk I used, right? Rewind to get the initial conditions. And actually, this is a hard question, and we figured out that the answer is yes, and you can recover half of the information, but not the other half. So this is very selective memory, actually. But I won't get into that. Okay. But I will tell you one last thing, if Sue will let me.
One thing.
Okay, one thing. There's a much easier way to rewind the dynamics to get back the initial conditions, right? If you look at the singularity right here, okay, the model that Wendy and Laura came up with is independent of what's above and below it. So each little slice through this neck is doing the same thing but at different times, right? The parts above and below are just behind a little bit. They're going to catch up. And so that means that if you are at the singularity, if you just move up or down, you're going back in time to what this looked like just a few moments earlier. And so the shape near the singularity recapitulates the history of this oscillation that we've been looking at. Okay, so what does that mean? If we do a disk of m equals 20, we should see that oscillation play out in the shape. So I'm going to skip this. And here's what you get. You get a pineapple. Okay, so you can see this 20-fold shape oscillating in and out again and again as you come away from the singularity. And you get this beautiful shape. So memory can be encoded in this shape. You can see the history of this whole thing just by looking at this shape in one picture. Okay, so memory is a language for history dependence. I showed you slow memories, and the cool thing about this is that if you are slow and noisy, you can actually learn more. And I also showed you fast memories, right? Singularities tend to erase memory, but air bubbles in water are an exception. And we can see how geometry and shape can encode memory, something you've seen already today. Okay, and I want to stress how we learned so much more about these systems by asking what kind of memories they had, and in some cases how they responded to cyclic driving, like we did with the rubber and the Mylar. Okay, and then my final piece of advice is stay away from equilibrium. Okay, thank you.
Oh, it's not on?
I just now turned it on. I just now turned it on. Just very briefly, suppose you're considering the universe and that's full, that has two things that would function as two different liquids or semi-liquids or air masses.
Okay.
What memory can you recover if you're talking about masses that are that big? Thank you very much. And if you don't want to tackle it, I sure understand.
This is actually a deep and long-standing question in physics, right? Is can you rewind the universe, basically? And the answer is, generally speaking, you cannot. The motion of atoms and molecules in most systems that are at room temperature, at finite temperature, are chaotic. The thermal motion is simply chaotic, and you simply can never acquire enough information about them to properly rewind things. Even though it is deterministic, I think for the most part, quantum effects don't really play a big role, but it's deterministic based on very, very finely detailed information, and you can never make observations that are that detailed.
Talking about the acrylic particles in the viscous fluid, you said when you introduce noise, that's when it shows that you can have multiple memory. Is that right?
Mm-hmm.
But you introduced a certain kind of noise. You moved the particles perpendicular to the shear. Is that right? Or
Yes.
So,
that's a great point.
So, what would happen if you actually introduced random motion? Would it remember just as well?
So for that, we have to use the computer, and the computer tells us that it remembers just as well. That doesn't mean that it works in the experiment, right? But the computer tells us we should expect it to. That's a great question.
All right, thank you.
Yeah. Yes?
Could you compare what happens to the shape of the air bubble or the water neck just before it snaps to what happens in a solid substance? Like you just pull it.
Oh, yeah.
Seal apart, right?
Yeah, like we didn't get time to get to the paperclip, but that's basically kind of what happens to the paperclip when it breaks. So I don't know if I'm qualified to really answer that, but it depends a lot on the mode of failure. So the paperclip breaks pretty much by fracture, right? So a crack just propagates through that and just splits it right in half in a way that you'd never be able to do with a pure fluid like water. But there are other solids that are much more ductile and plastic, where if you pull on them, they really will just start to get thinner and thinner and thinner in one spot and then break, and you'll get a sharp tip.
Is that just liquid in slow motion?
Whoa. I don't know. It can't be exactly like liquid in slow motion. But I think the idea of a runaway process is the same, right? That if you have, a uniform thing and it's a little thinner in one spot, well, that's the spot where it's going to get even thinner when you pull on it, and then thinner and thinner and thinner. So it's the same sort of runaway process.
In a material science lab, a stress lab, I've never seen it go to a singularity.
Okay, so I think that I've seen it. I just can't remember where.
You see the steel rod fracture.
Yeah, most materials will fracture because there are enough.
Generally starts with fracture before.
Yeah, there are enough defects there that you can sustain or start a fracture.
Well, glass, when you heat it and pull it.
Yeah, glass definitely.
Superfine tip, and that's how you make pipettes.
So glass is all defects basically, and but there you're starting to soften it so that it has some liquid-like properties. I don't know. Sid's probably apoplectic right now. You can.
I like to share with students how people get inspired to do certain pieces of research. So aside from the obvious, like your wife asked you to fix the dripping faucet in the bathroom, was there another motivation for this particular project?
I joined Sid's group, and he had been working on things like this for many years. So in some sense, you should ask him. But for me, like, why did I choose this project, and why did it really connect with me? And I think I'm just fascinated by this idea that you have this thing that's trying to erase information, and somehow you're fighting back against that, right? You have this process that preserves information, and it's really exceptional. And that just I don't know. I found that so cool, and I think also that having a background growing up, being exposed to computers and stuff like that, helped me to think in terms of information. And so that's maybe a mindset that really helps when you're thinking about memory.
And Nathan, your point about universality may answer this question, but I'll ask it anyway. If you have angular momentum in let's say both of your problems, the dripping faucet and also the air bubble. So the fluid is spinning. Angular momentum goes like mvr. So the r is going to 0, which might suggest it's not important. But you have to look at what v, with the the velocities also probably getting large, right? At this point. So it's not obvious to me that that's unimportant. But do you know if anyone's looked at that? Have you looked at spinning the fluid to see if you get the same phenomenon, the same universality class?
Other people have, and so it's a great question. It's an awesome question. I know other people have looked at cavity pinch-off in a spinning system. So you either spin the whole tank or you spin just the bottom of the tank. And I know that going to Irmgard talked about pattern formation, and you can get some beautiful, hexagonal patterns and so forth, all by, spontaneously arising. But that also has to do with the walls of the tank, because that plays an important role when you're trying to contain this spinning fluid. That's just a great question.
All right.
Yeah.
We'll take it off.
We'll take it with one more question, or yeah, we'll do one more question, then we'll.
Very quickly, what about a really viscous liquid? Like I've heard on the radio about a thing called the pitch drop experiment where they just watch. So just talk about that a bit.
Okay, so pitch, at least from what I understand, it is actually a Newtonian liquid, just with very, very high viscosity. Like, I don't even know, it's like 100 million times that of water or something. It has to be that high if it's going to take years to pinch off, where water takes milliseconds, right? And I think that, Sid, you can comment on this, but I think that they look at the dynamics, and it looks like what you would see just for any pinch off where viscosity is the most important thing. And so the shapes and the dynamics are the same. It's just
With angle or anything?
Nope. It's still universal. It's just really, really, really slow. But you could get the same thing by doing glycerin, right? That's also where viscosity is dominating.
All right. I think everyone's going to want to leave eventually, so let's thank Nathan for a great.
Thanks.